Good morning. We're going to give more free welding lessons. I think it's important also that people need to be introduced or have access to free education. Not everybody institute needs to get rich. So I'm going to give you some free welding lessons. I don't know if you can see that. It'd be easier if I just turn my camera down instead of me trying to raise up. So yeah, that's one lesson. Always try to make things easier for yourself instead of doing things the hard way. Try to find the easy way. It's not always being lazy. Find the laziest person to do the job and you're probably going to be the most efficient if the job ever gets done. But here's a little lesson for the beginners, and that's who I'm trying to reach, is the beginner welders. Somebody that's maybe welded a little bit in the garage, maybe they weld on a farm, maybe they have a weld machine laying around but they just are intimidated on how to use it. Maybe they don't know and they're just scared to touch it. Well, let me tell you, most welding machines that I've experienced, I've welded with a lot of machines, trust me. Every make and model, every brand. Some are good, some are bad, but they all generally do the same thing to some extent. You're not going to break a welding machine. They do break down, and you can burn them up, but it's difficult. You really got to be doing something wrong. You can't accidentally burn a machine up in your garage. Your garage will burn down before the machine will, typically. You can put a dead short on it, hook the two leads together, crank it up. It's going to kick out on the high limit thermal switch. It's going to trip a breaker well before it becomes a fire hazard, typically, not always. Look at this guy driving around over here. He's got his work light on. It's the middle of the day. Shining right in my eyes. He has no idea that light's on. Oh, he got them all on. All his backup side working lights are on. But yeah, so get free welding lessons from somebody that's a trusted educator. Not everything they tell you is going to be right or correct, but they're going to probably be spot on. But here's another little quick tip. These are the two most common welding rods you're going to see in the average welding industry. Now there's 1,000 different variations of welding rods, so don't take this as these are the only two welding rods. But here they are. This is your standard two welding rods, a light gray and a dark gray. They make different colors, but you've got a 6010 and a 7018. You got your cellulose 6010 and your low hydrogen. Iron powder, I believe, is what's on the flux on that one. These rods appear to be the same diameter, and this goes along with that lesson. Just because they look the same size, they're not. If you look down here, man, that doesn't focus very well. You've got a 332 rod and a 1/8 rod. The rod size is actually determined by the diameter of the steel. So if it would focus, you would see that this 6010 over here is actually a bigger rod than this one. Even though physically on the outside the flux is virtually the same, it may be a touch bigger on the 332 actually has a touch more flux on it. So it's actually bigger, but it's smaller. So be careful what you're doing. Learn your basic information. Like I say, these are your typical 7018 and a 6010. This happens to be a 6010 Pipeliner 6P Plus. It's a really good rod. There's a tip where you're going to strike your arc or initiate your arc. And there's that. This Excalibur's got a little bit of a, I don't know exactly what's on the end of it, but it's really good. Let's see if we can trick the camera. It strikes really easily the first time. That's another thing you'll learn. These don't like to restart. You got to kind of crunch the end off of it. It gets a slag, a ball of glassy looking slag over the end, and it's pretty tough sometimes. I usually take a little chip and hammer and keep it beside me and tap on it, re-break it. If I got some concrete or a file near me, I'll kind of wipe it and break that crust off of it. They do strike a little bit easier, but typically once you run this rod, let's say you run this rod somewhere down around these 3 marks, which I have no clue what these are for. I'm going to research that. That's probably just a manufacturer's mark. I don't know. But usually when you run this rod down, you get about halfway down, 3/4 of the way down. You've superheated this, and they typically don't like to restart. I don't know what it is, but I usually throw them out, get a new rod, start with a fresh rod every time. That's always going to help you. It'll keep you from getting porosity on your restarts sometimes. Start with a fresh rod, stuff like that. But there's a quick tip for the day. Just because they look the same size, they might not be the same size. But yeah, here's your low hydrogen rod, 7018. And they make these in a 8018, 9018. I've used 11018s before. Those are kind of special. You're not going to use those a whole lot. But your 7018 and your 6010s, your two most common rods in the industrial welding world. Certain other applications, they run some 6013s and different things like that. But for pipeline, we're going to run these. In the API world, a lot of these. So yeah, there's that. Quick tip for the day. We'll find some more tips. We'll add them in here later on in this video. This is going to be a multi-day conglomeration of different informations. We're going to have to find some more information for the free welding lessons. Stay tuned. All right, we've made it to the job site today, and give you guys a look at what I do on a daily basis. There's my rig, got our leads strung out. Everything's ready to go. And what we're going to do today is put on a punch tee, is what we call it. It's a 3/4 inch T and V valve. It's how you get the gas out of the main. We're renewing a service here, so we're going to retire one and install another. So it's awful bright and sunny. Show you guys the main and take a look see. Here's what we've got. We've got us a 2-inch steel main. We've got us a punch tee transition fitting. That's how you get your gas from a steel main to a plastic service. Pretty standard fitting. A couple different variations. This is what we use. So what we're going to do, we're going to weld that sucker right on there, and then once it's done, we'll run the punch down, energize the service after it's been tested, obviously. Make sure there's no leaks. We'll follow all the company protocol. But let's get this on there and we'll give you a look when we get finished. Low hydrogen in-service tee welded on the main. That is a live main. Got 54 pounds of gas in it. We'll talk more about the rod we're using. We're actually using a 7018 H4R, I believe is what it's called. We'll talk about that in a second. And there it is, the tee, the service tee and transition. Installed on a 2-inch main. Again, a little bit restricted because we had a small little hole. Let's see if we can zoom in. Oh yeah. So we checked it for undercut and all that, and then the service crew is going to come in, hook their plastic to it. They're back there. They're going to run a new service to this house. They'll test all this, wrap it, check it for corrosion and all that. Be good to go. So there's an average day on a service tee replacement. And as I'm ordering my lunch, I can't believe I'm doing this. It's sacrilegious for me. Yeah, having Taco Bell for lunch. Nothing wrong with Taco Bell, but it's just not authentic. It's not good. When you spend 6 weeks or 5 weeks in Mexico a year, Taco Bell just ain't it. It'll keep you alive. You're not going to starve to death. That's the main thing. keep you energized. But one thing I wanted to also put out there for any of the beginner welders, or professional welders for that matter, that, I don't know, just have issues or whatever, I think it's important that everybody knows that you don't have to make the prettiest weld every time. I'm not an artist like some of these TikTok, Instagram welders. They're truly artists. They're extremely good at what they do. They're exceptional at their craft. So good on them. I'm not an artist. I don't get paid by the appearance of the weld. The weld has to meet the criteria. It has to be a quality, sound weld. That's important to know, that some of you younger people maybe getting into this are anxious or have some apprehension about you're not going to be good enough, you're not going to be able to make the best welds, you're not going to be able to compete with these other welders out there. Well, let me tell you, you don't have to. You don't have to be an artist. You do need to make a good quality weld. It has to have quality-like workmanship. You got to meet the criteria. No undercut. You're allowed a very minimal amount of undercut, a 64th, basically, if you can catch your fingernail on it. It's a little excessive. You're allowed so much of it, a percentage of your weld. You've got some slag inclusion variances. You don't have to have a perfect weld every single time for the industry that I'm in, or the general industry. Nuclear code is probably going to be a lot more strict. Stuff like that. Aeronautical, aviation stuff, they're probably a lot more strict. Probably very low tolerance on discontinuities and things like that. So, but the general application for the average welder that's in a general pipeline industry, or piping, or steam, or API world, ASME world, there's some leeway there. So don't be too hard on yourself. Don't be doubting your abilities. If you can make a quality weld, you meet the criteria. Your cap's not too high, it's not too low, it's not too wide, it's uniform in configuration. You meet that criteria, you're good. So don't worry about making the perfect Instagram weld every time. I think that's a lot of things people get caught up on. These artists out there, they are truly artists. They're really good at what they do. Kind of makes people look bad, honestly. I wish I was better than I am, but I'm not. But I can still make a quality weld. It meets the criteria, passes the visual and destructive and non-destructive tests. The penetration on the inside is adequate. The tie-in is adequate. No misbevel, stuff like that. If you have stuff like that, you need to repair it. But yeah, don't be too hard on yourself. You're not making the picture perfect weld every single time. You get paid by the weld. You get paid by the hour. You make the welds quality. You don't have to be perfect every time. So let that be a lesson for some of these younger guys that are just starting off, and they're comparing their welds to other people's welds. Your welds will get better with time until a certain point, and you get to like my age, and it starts going downhill because you don't have the vision, you don't have the dexterity, you don't have the the flexibility, and you're not as agile. Things start to hurt. So at some point you will go downhill, but as you grow and as you come up as a younger welder in your late teens, early 20s, starting off, expect to get better as time goes on. So yeah, don't be too hard on yourself, and that's a good lesson. Watch people that know what they're doing, learn from what they're doing, try to mimic or replicate what the good welders are doing, but make sure they're good at what they do. Don't be cheating. Don't be taking shortcuts, because some welders will take some shortcuts and teach you some bad habits. But yeah, learn from an old guy and replicate what they do. But don't be too hard on yourself. You don't have to have the picture perfect Instagram weld every single time. There's a good lesson for the day. So I learned how to make it focus a little bit easier. But yeah, there you go. So you've got the flux is the same size virtually, but your rod diameter is different. So, oh man, we got to take a phone call. But yeah, there you go. We'll talk about what these rods do and how to use them in a second. We are back to our lesson. So low hydrogen rod, 7018. We'll start with that because everybody knows the 7018. All right, the Excalibur 7018. H4R. That's kind of an important thing in the pipeline industry, and what that means is if this rod is stored properly, which is very important. Why doesn't my window work? Huh. You got to store these very properly, cautiously. These, you're trying to keep them dry. Once you open that container, you need to keep them dry, keep them in a rod oven because they will absorb moisture. This rod here, if stored properly, should produce a weld with, I'm not going to quote that number, but it's 4 milliliters per gram, I think. I might be wrong on that, but it's 4 something per gram of weld material, I think, deposited. And that's important for hydrogen cracking, and that's why we use a low hydrogen rod. Fun fact. So this will help alleviate and reduce the chances of hydrogen cracking if this rod is stored properly and used correctly. Don't weld in the rain. Don't store these where they're going to get wet. If they do get wet, throw them out. You can rebake them, but I've never had much luck with that. Throw them in a rod oven, let them cook for a few days. I baked out some a while back and tried to use them, and they just weren't any good. They seemed to stick a lot, had a lot of spatter. Flux actually fell off of them. I think these were really wet, but yeah. So store your 7018s in a dry place. If you got a rod oven, you need to use that after they've been open for about 8 hours. They're supposed to be kept in a rod oven. So some inspectors, depending on what type of job you're on, they're going to be very critical of that. They're going to say, where's your rod oven? When did you open your can? If you got a tight quality control, your QC is going to really be watching that, so be very cautious of that. If you ain't buying the rods, it don't matter. Throw them out and get a new one. They're going to weld a lot better. They're going to have a lot less porosity and spatter. They're going to strike better. They're just going to be smoother. It's going to be a lot smoother weld. It's going to be a lot easier for you to control the puddle. So there's a good lesson. Always use a fresh, dry rod. So yeah, the H4R is a little bit higher quality, 7018. You can get some at the local hardware store, your big box stores, your orange and blue stores. You can get them there. Any of your farm tractor stores, you can get them there. But they're probably not going to be the H4Rs. So these are a little bit more expensive, probably. I don't buy welding rods anymore, so I really couldn't tell you what they cost. But if you're buying the name brand, you're going to pay for them. I tell you what I did do. I ordered some special rods for the test. They were fresh, Lincoln. I think they were Arc 80s. I don't know. I bought 3 different cans. I bought 50 pounds of the 1/8 inch 6010s and the 6P Plus. And then a can of a 50-pound can of the Arc 80s. Those were $5.32. And then I bought a 50-pound can of something else. I don't know if they were 7010s or 8010s, but 3 different rods. Is 150 pounds of rods. Cost about $1,000. It was $900 and something after our discount. We buy so much, they give us a pretty good price. So yeah, they was still almost $1,000 for 3 cans of welding rods. So these are highly specific. They are good quality, but they're brand new and they're dry. That's what helped me pass the test on my last test. So yeah, use a quality rod and know what you're welding with. So there's another lesson for the day. So we talked about the 7018, the H4R, and what that means, and the 4 somethings per milliliter, per 4 milliliters per gram of deposited weld metal, I believe. That's going to be keeping the hydrogen out. So that's what we use on an in-service weld. In-service means that you're welding something to that pipeline as that pipeline has a product flowing through it, whether it's gas, oil, petroleum of some sort, natural gas in my case. So we're going to weld service tees or pumpkins or repair sleeves, whatever you call them, things to the pipeline as it's live and active with product flowing through it. So you have essentially a cold pipe. You don't have the ability to preheat it, and you don't have the ability to get that moisture out of the metal, as they say, which is completely incorrect if you watched my last video. So there's no moisture in the pipe. What you're doing is you're trying to elevate the base metal, the temperature of the metal, and what that's doing is helping it off gas. You're doing a stress relief, so you're not quenching that weld instantly. You got a lot better chance of ductility. If you have a little bit of preheat, get you about 250 degrees. Get your parent metal up to temperature before you strike that arc, and that'll help it cool slower. That rapid cooling is where you get your fracturing and your cracking, and that's actually a couple different things. On the root pass, it's thin. Deposited metal is very thin on that root pass. You got thermal mass on your actual outsides of your welds. You got 2 big pieces of metal that you're trying to bring together. You deposit that root bead in there, it's awful thin. If you didn't preheat your base metal, then you're pulling that heat out really fast, and it tends to crack as that shrinks. And because of your rod selection, depending on what you welded with, you could have a heat affected zone that has a lot more dissolved hydrogen in it, which leads to hydrogen cracking. HAC, hydrogen assisted cracking, I believe is what they call it, and that's in the heat affected zone. It's going to make it a lot more stress, and your grain structure is going to be a lot different in your metal. I'm not a grainologist. I don't know anything about grain. I think they call those people metallurgist. I'm not a metallurgist, but I've heard a lot about it. I've read a lot about it, and you can study it if you're interested in it. It's a very technical, scientific field. So those guys are super educated. They're super smart. I don't have that capability, so I'm just a welder. They're going to tell me how to do it, what to do, and I'll actually do it. But you need to understand what you're doing, why you're doing it. So if you're welding something to a live line, you're not able to preheat it, you're going to use a low hydrogen rod, and that's why you're going to use your 7018s or your 8018s, or you're going to use a wire process. That's considered a low hydrogen process. So the gas that you use is going to create a environment that's low hydrogen. So either you're stick welding with the 7018, 8018, something like that, or you're wire welding, creating a low hydrogen process. And that's going to alleviate any cracks, hopefully. A lot less susceptible to the hydrogen cracking. You're going to have less hydrogen in there. So yeah, use the right rod for the right application, which brings us to the 6010. If you're bringing 2 pieces of pipe together, or 2 edges of metal that is not energized, not in service, you're going to run the pipeliner 6P plus. It's a 6010, and I think most people know, but I'm going to repeat it anyways. That's a 60,000 tensile strength material. So if done correctly, put that metal down, weld within the parameters that have been determined. This rod, this weld should have a minimum tensile strength or minimum yield strength of 60,000 pounds per square inch. The downfall of that is this is a cellulose rod, cellulosic flux. It's highly susceptible to hydrogen. It's going to produce a lot more hydrogen in the weld. I don't know the number, but I know it's a lot more than 4 milliliters. I don't know. This is going to produce a lot more than 4 parts of hydrogen. So you got to be careful when you do this. You're going to want to preheat your metal, your bevel, your 2 weld ends, your 2 pieces of pipe. Preheat those a couple hundred degrees. Make your weld, and then you want to keep your inner pass temperature elevated. Don't let that cool down. What you want to do is make your hot pass pretty soon. Don't let it cool completely. Get it welded again. Get your hot pass in. It's going to give you a little bit thicker root bead. Get a little more metal put in there, and then as you keep that hot, it's going to keep it from cooling quicker, and you're going to keep it at an elevated temperature, not thousands of degrees, but a couple hundred degrees, and that's going to bring that thermal mass up to temperature. And then when you are finished, it's going to cool a lot slower, a lot less stress, but you also want to get in there hot and fast. You don't want to be putting too much heat input in it. That's another thing. Your travel speed and your amperage has to be right to produce low heat input. Stick welding is very aggressive, a lot of heat input. It's not quite double the heat input of wire, I don't believe, but it's close, not quite. So if you're stick welding something, you got to remember you're putting a lot of heat in there, so you need to travel faster to get that heat input down to an acceptable level. And the smart people have already determined that, what's acceptable and what's not, what works for that particular application. We've got numbers we try to go by. You want to weld so many inches in so many seconds and at so many amperages, and that will keep your joules of energy input to an acceptable level. Because again, it goes back to your heat affected zone, and you're changing your grain structure, and you're trapping your hydrogen with these. So your open grain structure, I think, has a lot more susceptibility to the hydrogen getting caught maybe between the molecules. I don't really know. That's too technical for me. But imagine that you got some big molecules like basketballs, and they're all jammed together. You got some space between them, and that's where your hydrogen's going to go, in those little spots between the basketballs. Kind of like ping pong balls stuck between the basketballs. That's your hydrogen in the atoms or molecules, whatever those are called. But if you got a lot of that, then you got a lot of little opportunities for cracking, and it'll just go right on down the line, and you'll have a crack. And that's not good, because your pipeline breaks, and then your product comes out. It's dangerous. People get hurt, or you got environmental hazards, all kinds of stuff. So it's bad stuff. That's why it's important to follow the criteria. You need to understand the science behind it. Preheat your base metal, weld with this, and if you do weld with this, what we're going to do, we're going to allow that a couple days, 24 hours or better, to off gas before we wrap it. We talked about that. I didn't really explain that very well, but if you're going to weld with a cellulose type rod and you make that weld, you need to allow sufficient time for that hydrogen that's dissolved inside that weld metal to escape. So that's considered off-gassing. That weld, you'd never believe it, but it is actually off-gassing, because when you welded it, you trapped your hydrogen in there as it cooled. So you're going to have some hydrogen in there. You're going to let it cool, then you're going to let it off-gas. Now you can raise you can preheat that again, or post-weld heat treat. Elevate that temperature a couple hundred degrees, and that's going to allow a lot easier for that hydrogen to escape. A couple hundred degrees, that hydrogen is probably going to come out about 10,000 times faster. That's not a fake number, that's about a real number. So you have a lot better opportunity if you keep that weld elevated in temperature. That hydrogen gas is going to be able to escape and off gas a lot faster. Then when you put your coating on your pipeline, you don't have to worry about your off gassing creating bubbles under your coating. Now you got a bad coating. Now you have corrosion issues, which, as most people know in the pipeline industry, a lot of these things are cathodically protected, but you don't want bubbles under your pipeline coating. That's just bad. If you can prevent that by doing this correctly, you won't have that problem. And that's going to help your CP, your cathodic protection, out a lot. You're not wasting that energy jumping out them little pinholes that you've created and pockets, and you don't have moisture and all kinds of bad stuff going on. So it's very important to understand why you're using the rod you're using and how to use it correctly and what you're actually doing. There's a lot of science involved. A lot of smart people have discovered this the hard way, I think, over the last 40 years, 50 years. Technology's changed and the procedures have changed, and you got to be ready for that. But yeah, you got to choose the right rod for the right job. If you're in service, you're going to use a low hydrogen rod or wire, and if you're in regular old butt welds, bringing two ends together, a lot of people use this perfectly fine, but you got to do it correctly. You need to raise that base metal temperature, keep it hot, get your hot pass on before it cools, then do your fill and your cap, keep it warm, and that's going to help everything flow a little bit better, make it a little bit smoother. Everybody thinks that the 6010 is a brittle rod. It's not brittle. It's essentially the same metal. It's probably got a couple little different variances in there, but most of it is actually the flux. This is like an iron powder type flux. So this flux is a lot different than this flux. It's going to produce two different environments when you weld. I think a lot of this is consumed into the weld metal itself, maybe, where this is not. It's a little bit less. But yeah, so use the right rod for the right process and you'll have plenty of success. So there you go. That got very lengthy. I'm going to try to show some welds maybe sometime. But yeah, so there's your two rods. There's a 7018. It's going to crack and everything. So pretty ductile. It didn't snap. Again, here's your 6010. It's a little stiffer because it's bigger. It's very ductile. It didn't tear. So the metal's ductile. It's not a brittle metal. It's the process that you deposit that metal with determines if it's brittle or not, or if it's ductile. So yeah. So there's some more free welding lessons if anybody's interested in listening to me ramble for 12 or 13 minutes. We'll find something else to talk about soon. So it's kind of funny. I had a commenter on one of my other posts, which is, I think I've taken it down maybe. I don't know. I might repost it. But maybe it was on Reddit or something. Somebody was commenting on, I don't know why anybody would ever want to be an expert at MIG or gas metal arc welding or what else do they call it? Wire welding. Why would you ever want to be an expert at wire welding? Basically, a dummy can do it. I wouldn't say a dummy can do it. A dummy can do it, but can they do it correctly? There's a lot of things that have to be done to make it successful. But I'm going to explain to you real fast why I'm qualified to wire weld, and I'm an expert at wire welding. This is the simple fact. Yesterday was a prime example of why I want to be a professional and an expert at wire welding. Yesterday it was kind of getting windy, getting a little bit rainy, starting to have a little bit of overcast. I had a storm coming in. We had about 3 hours to get this job done. The job required a pumpkin to be put on, a repair sleeve to be put on a 2-inch main, had a leak, and we had 3 hours to do it. It just so happens wire welding will afford me that 3 hours to get that job done. If I decided to stick weld it, it takes about 6. So that's 2 hours I don't have to work. That's 2 hours I don't have to play in the rain. The mud was already coming up in the hole. The bottom of the hole got wet, turned into slop, and it's much easier to wire weld in that environment than it is to stick weld, because I don't have to lay in the mud for an extra 2 or 3 hours. So that's one reason you would want to be an expert or be qualified to wire weld or MIG weld, for that reason right there. It's 2 hours of efficiency, basically. It's faster. It's just as good. You can pass the same test with the wire or the stick, produce the same results. So that's another welding lesson for the day. There's our coupon. It's finally finished cutting. So yeah, yesterday was a prime example of why a person would want to be an expert at wire welding. Stick welding's not always the best, and that was another comment this individual posted. Stick is always better. It's always just as good. Well, I can assure you that you don't want to be stick welding a bunch of aluminum. It can be done, but you don't want to. So TIG might be the better option for that. So you want to have versatility in your abilities. You want to have different processes in your tool belt. You want to be able to pick up the wire gun, squirt gun, as some people, the old guys would call it, MIG gun, whatever you want to call it. You want to have that ability to pull that tool out, use the wire when you can, if it's applicable. If the conditions don't allow it, then you need to have the ability and the flexibility to switch over, get your leads out, put your stinger on it, and go to stick welding, shielded metal arc welding, technical term. So yeah, stick welding is better for certain things. Wire welding's better for certain things. If you're trying to control heat input, MIG's a lot easier to do that. So there's a reason to be an expert. So that individual was misinformed. He wasn't educated. I'm not going to say he's ignorant. Well, he was ignorant in the fact that he just wasn't informed. He's probably not a dummy. His ideas are pretty dumb, thinking that one process is the only process and it's always better. So that's a misnomer. So yeah, if you're ever trying to weld a piece of 45,000 stainless tubing together, that's going to be really tricky to do with the stick rod. So he's probably never tried that. If you're welding on heavy stuff, stick's fine. Some thin stuff, stick's fine. But yeah, everything has its application and has its own little advantage or disadvantage. So use those to your advantage. Don't lock yourself into thinking that one process is the best or always the best and good for everything, because it's not. There's different processes for different reasons. They've been created, and technology has changed over the years to allow for a better weld, faster and cheaper. And that basically means I don't have to work as hard, because I saved 2 hours of laying in the mud yesterday because I'm an expert at MIG welding. So there's a reason right there. So another free welding lesson for the day. Welding. All right, let's see what else we can do. We've decided to make a little weld here. We're gonna do a little test weld. Show you what we got here in just a second. It's a piece of 6-inch. I believe it's X52. I really don't know. We're not using this pipe for anything. It's scrap. It's just for testing and playing with, basically. So have a new welder maybe coming in here next few months or year or something. I don't know. They gotta get a new welder because I'm quitting. I hate this place. I think every welder has said that once or twice or 100 times in their career. I'm dragging up, I'm leaving. Sometimes they really do. I've seen them do it. But yeah, so we're gonna train us a new welder. At least he's gonna have somebody qualified in case something happens to me. So let's take a look at what we're doing. Here's the remnants of yesterday. We played in the mud again yesterday. That stinger does not go to that wire box. It looks kind of weird, but that goes over here. But here's what's what you're going to look like after you get done playing in the mud sometimes. This is what you got. We had mud all in the truck over everything we own. Got kind of sloppy, but there's my wire feeder box. But we're going to switch over again. We're going to do some stick welding. Like I say, we got a new guy that might be training. We're going to learn him how to stick weld first. MIG welding, wire welding is easier, so we're going to start with the hard stuff, and then once he knows that, then he will know how to stick weld, and then he can go right into wire welding, because I think he's got some experience with that anyway. So we got some 6-inch set up. Like I say, I don't know, I ain't looked at it. It might be X65, it might be X52, I'm not really sure. It's kind of thin, it's like a 188 wall, not real thick. We used our beveling machine, our air beveler, Tri-Tool 208B. Use that to put some nice factory bevels on, so it's got a cutter there. So if you have any questions, call them people, tritool.com. We use that to put some bevels on these pipes. We're just going to play and practice and learn how to do some stick welding. So here's a bead I put in. You can see it went in really nice, had a really nice keyhole, really tight gap, a little tighter than I like. It kind of closed up, but this machine that I'm using actually was able to force its way through there and get the bead inside. So that's the advantage of having a really nice adjustable machine. The XMT 350 is a super nice machine. It turned the arc force way up, and was able to force it right in there, and it just kept on going. So we'll tack up another one, make a short little test weld, and see what happens. All right, so we've been goofing around here, playing with some settings, playing with the machine. Let's see where we're at here. 70, and we've cranked our dig way up. We had a really tight gap on this one. We had a really fat gap on this one, so we struggled with that, and we forced it in with this. And again, we're welding the downhill, so we're gonna probably cut this out. I picked out a spot here on the downhill side. Let's see, it's not exactly on the side, but it's pretty close. So we're gonna cut this out here in a little bit and give it a bend test and see what it looks like. So let me finish this up. That was a 60-10 root with a really tight gap, about a 332 land. So yeah, we'll fill this up, hot pass fill and cap, and we'll take a sample out of that and see if it breaks. We'll prove them people wrong that say you can't weld downhill. So let's see what happens. And here's where we ended up. There's our cover pass. Had a restart right at the top of the edge there, so a little lumpy. But yeah, we're gonna cut this coupon out after it cools, and we're gonna give it a break and see if it breaks or bends or opens up, or see if there's any kind of inclusions or discontinuities inside there. So this will prove once and for all if you can weld downhill or not with the 60-10. All right, we got her cut out. I hope this don't look horrible on the inside. I'm gonna look like a dummy. That ain't too bad. Hopefully it's smooth when we grind it clean. So we're gonna grind this clean, grind it down, kind of round those edges off, and we're gonna put it in a vise and bend it over. We don't have a bending machine here. That's at the testing lab, so we're gonna do it the old-fashioned way with a vise and a hammer. And hopefully this doesn't snap in two and I look like a dummy. So let's see what happens. Let's clean it up. And we have brought this sample specimen to the vise. Here's the outside cap, been ground down almost flush. API, I don't think it's worried about the face. I think they're more worried about the root. So we've slicked it down. We got it ready. And I hope this thing don't snap. But you can see we're gonna try to bend it. Might drop it down just a hair. And then we're gonna whack it. See what happens. Let's drop it down just a hair and start hammering on it. See what happens. I was kind of concerned, but now I'm not. We was able to bend it over backwards on the root. This is the inside of the pipe. And this radius here is way tighter than what the API requirements are. Don't know, I'll have to find out what the exact dimensions are on their die, but this is much tighter. And if we look real close, I'm gonna try to get a good shot of it and see if it'll focus. You can actually see, oh, come on now. Come on, focus on that thing. You can see the actual weld ripples where it's stressed. You get the light just right. But we didn't have any cracks, we didn't have any failures. Nothing opened up. It didn't split on the ends, didn't split in the middle. Right there I see one little speck in the center. See that little bright spot? But I don't know what that is. It might be from where I whacked it with a hammer or something. But yeah, this proves once and for all you can weld downhill with the 6010. It's not brittle. I don't know why people think they call it brittle. Well, it's not. Let's zoom in, see if the zoom will change this. See if it'll focus. Oh yeah, there it is, much better. So you gotta learn, you gotta be smarter. You gotta learn what you're dealing with. But there's the weld. And if I didn't screw up my acid last time, I'd be able to put acid etch on there. You'd be able to see this a lot more clear. But there's your weld ripples. That's each little movement that I made is forever locked in there in that metal. So yeah, this was a downhill weld. And this is the inside. This is the root. You can see the stress that was on that pipe that's in there. But yeah, no failure. I'm proud of myself. We passed again. There you go. There's what you can expect to see with the API test. This is actually more extreme than that. But yeah, it can be done. You can weld downhill with the 6010. It's not brittle. It is ductile. So give it a shot. And there's another lesson for the day.